Take this particle, make it the opposite charge, turn it the other way, but it's not the antiparticle, it's the other antiparticle, right? It's this other one, but then you gotta take it, flip it around, shove it in a hole, right? And then we have a cute little acronym that we call it, right?
Hey Crazies, welcome to another installment of Wife Reacts. This is my wife, Awkward M.
Hello.
Today, I'm gonna be explaining dark matter to her. Let's see how this goes. Okay, so first off, I guess, what exactly do you know about dark matter? Just so we can get a baseline here.
It doesn't emit light. There's a lot of it.
Yes.
I know that Vera Rubin is an important lady. I think that's it.
That's about it, okay. But before I get into this, because I know there's going to be a bunch of people that are going to mention this in the comments, you know who you are. It is entirely possible that we don't understand gravity as well as we think we do.
Sure.
That is possible. But the ways in which we would have to change our models of gravity to explain all of the things that dark matter explains is, it's absurd.
It is actually less work to just accept dark matter.
Right. And so it's possible that we don't understand gravity, and it's possible that maybe one of the things that we attribute to dark matter could just be explained by modified gravity, like one thing. But not all of them.
Sure.
And so most models that include some kind of modified version of gravity also include dark matter because they know that it can't explain everything.
Okay. So we're not saying that modified gravity doesn't exist at all.
Right.
It just is not a full explanation of all of the effects of dark matter.
Correct.
Okay.
All right, so then the question remains, what exactly is it? Prepare yourself for some acronyms.
Oh, love a good acronym. Here we go. Oh, they're the silly ones, aren't they?
Yes.
Oh, no. Okay.
Candidate number one, machos,
Right.
which stands for massive and compact halo objects.
Okay.
The halo is a region of the galaxy outside of the disk.
Oh, the side of the disk.
The galaxy is spun into a disk, a spiral disk, which is where most of the luminous matter is. And then the halo is everything outside of that. Now there are things out there like...
Didn't know there were things out there.
There are things out there, like they're called globular clusters. It's these
Okay.
clusters of stars that are really densely packed. There are these objects that are in the halo of a galaxy, and they're massive and compact. So we're talking things like rogue planets, white dwarfs, neutron stars, black holes.
Yes. Comfortable with that.
Those are all considered massive and compact halo objects, or machos.
Okay. Okay. Okay.
These are all very ordinary things, right? We wanted dark matter to be ordinary things that we just weren't seeing.
Sure.
The problem is, we can do rough estimates of
Right.
ballpark order of magnitude estimates of how many of those things we expect to find. And it's nowhere near enough. The rest of it, the rest of the 84% of matter that is dark matter, has to be something more exotic. Based on our evidence of dark matter, it has a few properties that we can say conclusively about it. Now we call it dark matter, but it should really be called invisible matter. It's actually legit invisible. It doesn't interact with light at all.
It does not block out the light if the light is behind it.
Right.
Like you would expect for like a planet or something like that.
Exactly, or some like dense, dark, nebulous cloud. It's not like that. It must not interact with light. We usually say at all, but technically it could a little bit, but in a way that's below our ability to detect.
Which is weird.
Yeah, that's weird, and it's a
Yeah.
lot lower than normal matter would interact with light.
Sure.
And if it doesn't interact with light, it's not electromagnetic at all. That means we can't put it in a container either.
Why?
Because the reason that your hand doesn't go through things is because of electric repulsion, right?
Oh.
The electrons in your hand.
From your subatomic particles.
Exactly.
Okay.
We know that if it doesn't interact electromagnetically, then it doesn't do that. And so you couldn't put it in a container. It'll just pass right through the walls of your container. Not only can it not be seen, it also can't be held.
Do we have dark matter in our galaxy?
Absolutely. We have dark matter in our solar system.
So I think that already shows us that like we can't interact with it because
Right.
it's apparently here and yet
Now, there isn't much of it.
Uh-huh.
We know what density we should expect it to have. And that density is extremely small. We're talking like if you took all the dark matter in our entire solar system out to Neptune's orbit and you collapsed it into an object,
Okay.
it would have the mass of a medium-sized asteroid, which
Okay.
is very small,
Okay.
astronomically
Honestly,
speaking.
bigger than I was anticipating based on what you were saying.
That's pretty small, astronomically speaking, right?
Okay.
But if it doesn't interact electromagnetically, then it wouldn't ever form an asteroid.
Right. Why would it?
That electromagnetism is what slows things down and generates heat and like saps energy away. And so if it doesn't interact electromagnetically, then it doesn't slow down, which means it can't clump. The best we can do is just a diffuse cloud of it. A cloud of stuff that can't be seen and doesn't interact with anything, except gravity.
Invisible.
Hence invisible. So we can only see it based on its gravitational effects.
I mean, but have we actually found its gravitational effects in the solar system?
No.
No.
Because there's not enough of it.
Okay. That makes sense.
Asteroid mass isn't going to do much to our solar system, which is why we don't see it here. And we don't see it on a stellar scale either. It has to be an interstellar galactic scale before we start to see its effects.
Okay.
Before the scale is large enough that there's enough mass to actually do something. While technically the dark matter is here and it is gravitationally affecting things, it's not really that much. There's much, much bigger influences.
Okay.
Our next category, next candidate for dark matter, they're called WIMPs.
Okay. Who named these?
Right.
You needed like.
I think they're the coolest acronyms in astrophysics, hands down.
Nick's over here like.
So WIMPs are weakly interacting massive particles. They're not big, compact objects. They're little tiny particles, and there's just a lot of them.
You know what I think I'm really struggling with? Massive. How can something have mass if it doesn't interact electromagnetically?
What gives you the impression that something has to interact electromagnetically to have mass?
Because generally we say that things that have mass are made up of particles. I'm thinking that in order to have mass, you need some protons, neutrons, and electrons.
Which is not true. It doesn't have to be electrons, neutrons, and protons, or quarks, or whatever, right? There are a lot of particles in the Standard Model, which is gonna be a big deal today.
This the...
Yes.
Okay.
The big chart.
You want to throw that up for them?
Definitely gonna happen. So there's a short list of elementary particles, and then there's a whole long list of particles that are made from those particles. Like protons and neutrons are not on the elementary particles list.
Fair enough. I'm a biologist, okay. That's as far as I need to go.
They're made of smaller particles called quarks. But those quarks only represent about 1% of the mass of a proton. The other 99% is actually made up of massless particles called gluons.
I don't like it. I
And
don't
so
like it at all.
99% of the mass of a proton is from massless things. The whole concept of mass, it's very different on a quantum level than it is on a normal level.
Different is such a polite word for it.
Try to leave some of those preconceptions, try to set them aside.
You can take that out of my cold dead hands. No, all right.
You can
I'll
say,
accept it. I will accept that it is massive, even though it is not made up of particles, or it's maybe made up of particles that don't have mass, or
Right.
whatever.
or they do have mass, but they don't have any charge. And if they don't have any charge, then they can't interact electromagnetically.
Oh, so they could be neutral.
Yes.
Okay, I'm comfortable with that.
Now, neutrons do interact electromagnetically, even though they're neutral, because their parts aren't. The quarks have charge, even though together they form a neutral particle.
That makes sense.
If we want dark matter to be one of these WIMPs, one of these weakly interacting massive particles, we need to make it a massive particle that's an elementary particle
Okay,
that isn't made of charged parts.
right. Okay, I accept this. It is made of particles.
Yes.
Just a neutral particle that is not made up of any other charged smaller bits.
Like neutrinos. Neutrinos could be dark matter because they are massive. They have mass, not very much, but they have mass and they don't have any charge. They're neutral, that's why we call them neutrinos.
Okay. But they do interact with something because we can...
Detect them.
That's the word I'm looking for.
Right. We do have neutrino detectors, and there's the big tanks full of oil, basically. These neutrinos are tiny. They're a tiny amount of mass, and they are very weakly interacting. So even though we have these giant tanks full of oil, they only detect 1 or 2 neutrinos a day. But there are 100 trillion neutrinos passing through your body every second.
That's invasive.
Just passing
Back
right
up,
through.
neutrino. I did not consent to this, okay?
But they're not just passing through your body, they're passing through the Earth.
Right.
So these neutrino detectors detect neutrinos from all directions, including down. Some of these neutrinos pass straight through the Earth and then hit a molecule in the oil. And based on what that interaction eventually emits, we have detectors around the outside of the tank, and we can determine not only the energy of that neutrino, but what direction it came from. So we can know if it came from up or down. We've got something built into the standard model that could be dark matter.
So it's not that it doesn't interact, it is that it weakly interacts on such a small scale that it's not meaningful until you have a lot of it.
Right. We've got these things called neutrinos, right? And they fit the bill. They match what we expect dark matter to be.
Right.
Almost.
Oh, no.
Most neutrinos are traveling very, very fast, like near the speed of light. And so they're carrying a lot of energy, kinetic energy. And that is not something we expect dark matter to do.
Carry kinetic energy, or a lot of kinetic energy?
Carry a lot of kinetic energy. Anything that has mass and moves around, anything that moves around at all has kinetic energy. Even photons have kinetic energy. When we model what we expect dark matter to look like, we expect it to be something we call cold dark matter. And by cold, we just mean not moving fast.
Interesting use of words.
It's kind of analogous to how thermal energy works. When things are moving really fast, it's hot, and when things are moving slowly, it's cold. And so it's kind of just
An homage to that.
Yeah, we're using hot and cold analogously like that.
And so that makes sense that absolute zero on the Kelvin scale, can I say that?
Yeah.
Kelvin scale is a complete absence of movement.
Right. Aside from some weird quantum uncertainties, yes. Because nothing can ever be exactly zero. But yeah, so we expect most dark matter to be cold, not moving very quickly. So most of the neutrinos we see don't actually fit the bill. They might be dark matter, but they're not cold dark matter. Now this doesn't rule out neutrinos though. There are slow-moving neutrinos. We can't detect them because in order for them to actually, like the more energy they have, the more likely they are to interact in our detectors.
Fair enough.
And so we can't actually detect the slow ones.
But the idea checks out mathematically.
Right, and we do expect them to exist. We know that whether or not a neutrino is affected with the weak interaction is determined by whether or not it's spinning clockwise or counterclockwise, whether or not it's right-handed or left-handed.
Okay, so only one, like only left-handed or only right-handed will interact with the weak interaction.
Yes.
Okay.
You're familiar with that matter has an antimatter partner.
Sure.
Okay, well, each one of those, the matter and the antimatter, can spin 2 different directions. You can have the matter spin clockwise or counterclockwise, and you can have the antimatter spin clockwise or counterclockwise. Only one from each set is affected by the weak nuclear interaction. Left-handed regular matter is affected by the weak nuclear interaction, and right-handed antimatter is affected by the weak nuclear interaction. But the left-handed antimatter and the right-handed regular matter are not.
Sure.
They're called sterile.
Okay.
Because they don't interact with the weak force.
Got it. What's complicated is that we've talked about so many particles at this point that my brain is like, I don't even know what particles we're talking about.
I was worried about this.
I am particle overloaded.
This is why people are like, that's ridiculous. Because this is what it's out. There's so many different little things.
You're like, take this particle, make it the opposite charge, turn it the other way, but it's not the antiparticle, it's the other antiparticle, right? It's this other one, but then you gotta take it, flip it around, shove it in a hole, right? And then we have a cute little acronym that we call it, right?
Yes.
And it may or may not be real, we don't know yet.
No, these are real, okay?
Thanks for letting me get that off my
Yes.
chest.
But if the sterile neutrinos don't interact with the weak force, and we already know they don't interact electromagnetically, they're only gonna interact gravitationally. They'd be considered a weakly interacting massive particle. And we do have a tiny, tiny bit of evidence from our neutrino detectors that they do exist. There's enough evidence to hint that they do.
There's enough evidence to say that we should study them more.
Yes, absolutely. But the point is, we know that dark matter has to be there. It doesn't have to be one thing. It could be a combination of all of these things. But the point is that the overwhelming majority of this effect must be matter. We know that it's matter.
Because it's massive.
Right. When things are massive and they can move around, that's what matter is.
Right.
Right? And so we know that it's matter. We just don't know exactly what type of matter it is, and it could be a combination of things. But in terms of the two broad categories, in terms of machos and wimps, we expect dark matter to be overwhelmingly wimps. Thanks for liking and sharing this video. A special thanks goes out to all my generous Patreon patrons and YouTube members for making all this possible. Don't forget to subscribe if you'd like to keep up with us. And until next time, remember,
it's okay to be a little crazy.
If the Earth could fit in your hand, it would be heavy. Yeah, I mean, subjectively, sure. If you kept the Earth the same density, it would be a fairly smooth sphere with a weight somewhere between aluminum and steel. Some people might call that heavy. Anyway, thanks for watching.